Here is where the rubber meets the road for redox reactions, because redox reactions are a very important part of our lives, specifically in the area of batteries. A galvanic cell is a type of a battery, and a galvanic cell takes advantage of the fact that a lot of redox reactions are spontaneous. And so, as we've seen, in a redox reaction, you're going to transfer electrons from one reactant to another. And when electrons are moving from one to the other, what is a flow of electrons? Well, it's electricity. And so a galvanic cell can take advantage of a spontaneous reaction to harness that flow of electrons. And then you can use that flow of electrons to power something that requires electricity. Now, again, the workings of a galvanic cell and how they're all set up, and which piece is oxidation and which is reduction. You probably, again, had most of this in your first year course. This is something that can very easily get rusty, and so we're going to go through it in detail to make sure that you haven't forgotten any of that. If you have, you'll be able to very quickly relearn it again. So when we start out a galvanic cell, and you've already done this experiment, and so you've built a galvanic cell already, but you know that there are two separate containers required, because if you put the reactants together, they're just going to start reacting immediately, and you won't be able to use that flow of electrons to power something else. So in order for us to be able to harness that electricity, we do have to have two separate containers. And so I'll start out by drawing my two separate containers up here. And you're gonna have to draw a lot of galvanic cells, so you'll want to make sure that you can get in the habit of doing these well. Okay, now we already know that in a redox reaction, you have two pieces to it. You have oxidation and you have reduction. And so we also are gonna call each one of these containers something different. We're gonna have the anode, and we're going to have the cathode. Okay, now the anode is where oxidation takes place, and the cathode is where reduction takes place. So the oxidation happens at the anode, and you will notice, here's the way I remember that. Anode and oxidation both start with the vowel. Reduction takes place at the cathode, and C and R are both consonants, and so they both go together, okay? The other thing that you need to remember about the anode and the cathode is that the cathode is generally considered the positive end, and the anode is considered the negative end. And how do you remember that? Well, I guess if you're a cat lover, you can say, well, cats are positive. Okay, if you're a dog lover, sorry, it's the best thing I could come up with. So the anode goes with oxidation, the cathode goes with reduction, two vowels, two consonants, okay? Now, I will also tell you that, once again, the author's not super consistent in how he draws his cells. Sometimes he has the anode on the right, sometimes he has it on the left. For me, it's much better to always be consistent in how I draw them, because it helps me to keep the flow of electrons straight. And so I always want to put the anode on the left and the cathode on the right. And I'll show you why in just a second. But again, here I got them in alphabetical order. The anode comes first, followed by the cathode. A comes before C. So I'm going to put the anode first, okay? When I do that, then it's much easier for me to be able to determine and to remember what the flow of electrons should be. Now, in each container, you're going to have an electrode, usually is some sort of a piece of metal that's going to be involved. And you're going to have a wire that's attaching those two. And because oxidation, remember Leo says grr, here, because I'm losing electrons over here and I'm gaining electrons over here, the electrons are going to have to go from this container to this container over here. So my electron flow goes this way. This is why I like to have the anode on the left and the cathode on the right, because the electrons then go from left to right, which is the same direction that I read. And so going from left to right seems to me to be normal. And so therefore I want my anode here and my cathode here so that that's the way the electrons are flowing. Okay. Now, what happens if I end up with so much electron flow? I'm losing tons of electrons over here. What's going to happen to the overall charge of this container? If you lose electrons and you lose electrons and you lose electrons, yeah, eventually it becomes very, very positive, and these electrons aren't going to want to flow anymore. And so a very important part of a galvanic cell is that you also have something called a salt bridge here in the middle. That's where we draw that. The salt bridge contains another compound that is not going to react with anything else that's in either one of these, but its whole purpose is to supply ions to balance the charges out. And so within the salt bridge, if the electrons are going to be flowing this way, then the negative charges in the salt bridge are going to flow the opposite way. If I'm taking electrons and making it go this way, this becomes more and more and more negative. If I want the reaction to keep running, I'm going to have to take the positive charges in the salt bridge and send them this way. Okay, so that's the purpose of the salt bridge. The salt bridge is going to keep the charges more even and more balanced so that in each one of these containers, the reaction is going to be able to keep going. Okay. These are going to be happening in some sort of solution almost always. Now, sometimes we're going to have some gases that are involved, but gases can dissolve in water, so that works okay. Let's go ahead and put some half reactions with this. Let's say that on my anode side, I have nickel in the solid form, and it's going to be losing electrons to turn into a nickel +2 ion, okay? It's lost electrons, oxidation, okay? So on this side, the electrode here is going to be made out of nickel, and then I'm going to have nickel-2 ions in solution. On the other side, let's say that we've got silver. Let's say that I have silver ions, and they're going to gain electrons and then become, this is aqueous, this one was aqueous, and then this is going to be solid, to become solid silver. So on this side, I'm going to have silver ions in solution, and my electrode is going to be made out of silver. Now, the electrode does not always participate in the reaction. Sometimes it does, but sometimes it does not. In this very simple example, the electrodes are going to participate in the reaction. So, as nickel turns from solid nickel into nickel ions, the electrons are going to flow over here. As those electrons flow, the silver ions in solution are going to pick up the electrons, and they're going to turn into solid silver, and they're going to just attach themselves to the electrode. So as time goes on, what's going to happen is the nickel electrode is actually going to decrease in size because it's going to get used up, and the concentration of the nickel ions is going to increase because I'm losing electrons and forming this. Now, what happens on this side? Well, as the electrons flow, the silver is going to pick up those electrons, and it's going to turn into solid silver. So here, the silver electrode is going to increase in size, and the concentration of the silver ions is actually going to decrease. Okay? So, there we have a galvanic cell all set up, and we can see how that works. Each half reaction now also has a specific tendency to happen. We talked about how some reactions are very likely to happen, others aren't so likely to happen. Some of them go to completion, some of them don't go to completion. We spent lots and lots of time talking about that. Well, it's the same way in electrochemistry. Each half reaction has a specific tendency to happen. And if you look in the back of your textbook, on the inside of the back cover, and there's one in the middle of the chapter too, but on the inside of the back cover, this is actually the easiest one to find. You will find a standard reduction potential table to use. You do not have to memorize this. You can use this in all of your problems. You'll be able to use this exact same table on the test. Okay, so you will need to use that. Let's look at the right-hand side of the table first. And you will see that everything on here is written as a reduction reaction. Everything on here is gaining electrons because that's what reduction is. We're gaining electrons, right? And so if you focus on the right-hand side of the table, what this means is how strongly are these reactions pulling on the electrons. And so on the bottom, you can see that fluorine has a voltage of 2.87. So that's got a much, much stronger pull there than if you look at the very top where you've got tin and that just has a voltage of 0.15. So down at the bottom, that's a really, really strong pull on the electrons, where at the top, it's not. Now, if you look on the left-hand side of the table, you can see that all these values are negative. And so what that is telling us is that all the reactions on this side of the table really don't want to happen because it's a negative number. They would prefer to be oxidized. They would prefer to be running in the opposite direction. And so these guys are really pushing electrons away from them with the way that it's written in the table. And so at the bottom, because that is 0, in fact, everything on the table is compared to this hydrogen, there's no push and no pull at all as well. And then the very top of the table where you've got the potassium, that's a very, very strong push away. Now, we're going to get more into determining what's a good oxidizer and what's a good reducer in Module 10 and not so much here. But for right now, what we want to be able to do is determine what the standard reduction potential for the cell is. So if you look, I have two reactions here. If you look on the right side of the table, about halfway down, you will find this reaction right here, and it's written in the same order as what I already have there. So the standard reduction potential for this is 0.7991 volts. Okay. If you look on the left side of the table, you will also find the reduction potential for nickel. It's most of the way down, and you will see that that is a negative 0.250, but you'll also see that that's written the other way around. This part is on the left, and this part is on the right. Well, just like with the reactions that we've seen before, if I take the reaction and reverse it, all I have to do is take the reduction potential and I can make it go from negative to positive, and that will give me the reduction potential for this one. So in the table, it says negative 0.250. And so for this reaction, since I flipped it around, it's going to be a positive 0.250 volts. So what that means is that for the entire cell, the standard reduction potential for the cell, and that's how we write this, and he doesn't write it this way here. He kind of adds this in the next section, but this notation is one that you're going to see again. So the standard reduction potential for this entire cell then is the 0.250 volts plus 0.7991 volts. And so therefore, the standard reduction potential for the cell is 1.049 volts to the proper number of significant figures. Whoops, there went my pen. Okay, so here's the standard reduction potential for the cell. Okay, so that's how you calculate that. However, do you see a problem here? Well, what is the case here is that how many electrons did this nickel give up? It gave up 2, right? How many electrons did this silver gain? It just gained 1. That's not balanced. We've always said that we have to balance our reactions, okay? So what that means is that in order to have a balanced final reaction, what I'm going to have to do is I'm going to have to take this entire reaction and I'm going to have to multiply that by 2 to get my final reaction. So when I multiply that reaction and I add those 2 reactions together, what I'm going to end up with is this. I'm going to leave the nickel as it is. So I'm going to have nickel. And just for simplicity's sake right now, I'm going to leave off the phases and, until I get to the end here just to simplify things. So that's going to give me nickel, positive 2, plus 2 electrons. I need to multiply this equation by 2. So I'm going to have 2 silver ions plus 2 electrons yields 2 silvers. Okay? Now, just like we can do in algebra, I can add those equations together and you'll see that I have nickel plus 2 silvers plus 2 electrons yields a nickel 2 ion plus 2 silvers plus 2 electrons. I have 2 electrons on both sides of the table. So those are actually going to cancel out and you can't see that, can you? Let's fix that. So you can see that bottom. Okay, so we've got 2 electrons on each side that are going to cancel. And so therefore my final reaction is going to be Ni, and now I'm going to go ahead and I'm going to put the phases back in. Nickel plus, I forgot the ion charge up there, plus 2 silvers will yield Ni2 plus aqueous plus 2 silvers solid. Okay, now I want to point something out to you, and that's that you will see that the nickel, there's 1 nickel atom on each side and there's 2 silver atoms on each side. Okay, again, this is an idea that we're not going to explore really fully until we get into the next module, but you will also see that I have a total of a positive 2 charge on this side because of the silver ions, and I have a total of a positive 2 charge on this side because of the nickel ions. In a redox reaction, not only your atoms have to be balanced, but your charge has to be balanced also. It may have looked before that I could take nickel plus silver yields a nickel ion plus silver, and the number of atoms would have been balanced, but the charges would not have been because there wouldn't have been a 2 in front of this. So when you finish this up, you should be able to look at it and say, okay, yep, all the atoms are balanced. Yep, the total charge is balanced as well. Again, we won't really get a whole lot into that until module 10, where we're balancing redox reactions, but it's an idea I want to introduce and get you used to the idea of looking for that because both of them have to be balanced in order to be able to work. Okay. All right. I am going to go ahead and do example 9.4 for you because I realize that's a whole lot of material and maybe you need to see another example just to make it all make sense. So I'm going to erase all of this and we won't have nearly so much to write in the next one. We're not going to draw a Galvanic cell out for that problem. I'm just going to be analyzing what the actual reactions look like. Okay, now we have some space to work with. We have 2 reactions. At the cathode, we have a gold ion. Is it gold? Yeah, we have a gold ion. Fancy stuff. And I'm going to add 3 electrons to that to get some solid gold. And then I also have tin, which is going to go to a positive 4 charge. and I'm going to have 4 electrons for that. So that's what's going on in the reaction with the following half reactions. And so they want to know the overall reaction, and they want to know the voltage for the cell, okay? So the overall reaction, first of all, again, I have one of each of the elements, but look at my electrons here. I'm gaining 3 electrons, but I've lost 4. That's not going to work. So I'm going to have to take this whole reaction and I'm going to have to multiply it by 3. And I'm going to take this whole reaction and I'm going to multiply it by 4 in order to be able to have the same number of electrons on both sides. Okay, so when I add this together, I'm going to have 4 gold ions. I already can see that these electrons are going to cancel out, so I'm not going to write the electrons because I can see that I've got 12 electrons on this side of the arrow and 12 electrons on this side of the arrow, so I'm not going to write those again. So on the left side of the arrow, I've got 4 golds and I have 3 tins. And then on the right side of the arrow, I'm going to have 4 gold atoms and 3 tin ions. Okay, so I can double check and make sure it balances. I've got 4 golds on each side. I've got 3 tins on each side. Here I have a positive 3 charge and I have 4 of them, which makes a positive 12. And here I have 3 positive 4 charges, which again makes a positive 12 charge. So my atoms are balanced and my charges are balanced on each side. Okay, it also wants to know what the voltage is for the cell. And so if you check the standard reduction potentials in the back, you can see that the gold is most of the way down on the right-hand side. And you can see that it's exactly the same as we already have it written there. And so the reaction potential for this one is 1.50 volts. And for the tin is on the top of the same side, but because this one's adding 4 electrons on the left and this one has the electrons on the right, I have to take this standard reduction for the half reaction and I've got to make it negative. So this E sub 0 is going to be negative 0.15 volts, okay? Don't get confused. This is not like like the Hess's law problems where we did. You do not multiply these by 3 and by 4. You just use them straight just as they are. They do not get multiplied. So when I add these together, the standard reduction for the cell is just 1.50 plus a negative 0.15, which is going to give me a 1.35 volts. Okay? So, phew, that was long. But hopefully you can kind of see now how all these pieces fit together. You can see how a galvanic cell is put together. You can see how to determine the voltage for it. You can see how to determine the overall reaction for the cell, that both number of atoms and the charge both have to be balanced in order to have a balanced final reaction. So you'll get to do some practice on this in your homework today.